Happy Star Wars Day, everyone. I am so thrilled to have you with us here where we get to geek out a little bit about Star Wars and binary numbering. So I've got a very Star Wars themed session for us today, so hopefully you're a fan. And I think we're going to be having a lot of fun because I'm going to have some Star Wars themed exercises for you to do a little bit later on. We're going to actually be competing for some prizes, so I think you'll enjoy that. And just once and for all, handle this topic that I've been teaching this stuff for like 3 decades. This is probably the most challenging topic that people get tripped up with because it gets a little bit mathematical. And just to be super honest with you, I understood subnetting a little bit when I got my CCNA. I really struggled with it when I was getting my CCNP. I had to play with the binary numbers a little bit, and I could finally get an answer usually. But it didn't really click. I didn't really get it until I was studying for my CCIE. That's where it really clicked. And I've, since that time, taught it for over 2 decades now. And I've really tried to simplify it. And today I want to share with you a 3-step process. And this is my goal for you today. I want to share with you a 3-step process where I can say, here is an IP address and a subnet mask. And within a minute, you're going to be able to say, oh yeah, it lives on this network. That's going to be tremendously helpful for troubleshooting. It's going to be tremendously helpful for design in your networks, because when you take a network address space and you chop it up, you need to know what IP addresses to assign in each of those subnets, what IP addresses are valid. And that subnetting topic really deals with IP version 4, but yes, IP version 6 is here, and it's growing all the time. So we'll take a look at hexadecimal numbering that's used in IPv6. And let's go ahead and get started right now as we dive into our content with just a quick agenda overview. We want to talk about IP version 4 subnetting, and to do that, we're going to have to review a little bit about the IP version 4 address structure. We're going to have to understand the different classes of addresses, because that plays into our calculation. As we're doing our calculation, we have to know, is this a class B network? Is it a class C network? What is it? But if you stay to the end of class, I'm going to give you a link to download a PDF, and this PDF has 12 subnetting questions, and we're attacking it from all different angles. So if you master these 12 questions, you're going to know subnetting as well as you need to know it for an exam and for the real world. So I'm going to give you the steps today. The light bulb's going to come on for many of you today, I hope, but you're really going to ingrain it by going through those practice questions. And I'll be giving that to you at the end of class. Now, for those of you that don't know me, just a super quick bio since we're going to be spending the next couple of hours together. My name's Kevin Wallace, and been doing this for a while. I got a couple of CCIEs, one in enterprise infrastructure, one in collaboration, and just recently, about 2 years ago, I hit my 20-year mark as being a CCIE, and I'm now what they call a lifetime emeritus, which means I don't have to recertify anymore. So that's a big relief. I've been working with Cisco gear since the very first Cisco router model back in 1989. It was the old Cisco AGS Plus router. I worked for Cisco Learning Partners for about 14 years. I was a network designer, one of 5 network designers down at Walt Disney World in Florida. And that's where I got up. I'm a huge Disney fan, by the way. I'll go ahead and tell you that. And I got to design or redesign the network that interconnected the Magic Kingdom and Epcot and the studios and Animal Kingdom and a bunch of the resorts. Just a great place to work. In our training, we often work in some Disney stories throughout. Wrote a bunch of books, did a bunch of videos for the folks over at Cisco Press, spoke a couple of times at Cisco Live, and the bottom line is, I love this stuff. I've been doing it for decades. I'm passionate about it, and I cannot wait to share it with you. Now, I said we're going to have some Star Wars theming today. I thought you might not be able to see everything on this little tiny thumbnail you have of me right now. So just for a second, let me kind of show you how I've almost said how I've decorated the studio, but it's like this all the time. Let me show you what's going on here in the studio, Star Wars wise. We've got, let's see, behind me, here's a little Cincy candle. You might be able to tell that's Cloud City with TIE fighters going over Bespin. I've got some of these Coke thermal detonators that you get at Galaxy's Edge. Let's see what else we have. We've got a Porg up there. We've got BB-8. You can't really see what that is, but that's a Kylo Ren doll. And this is the Jedi Files book. You open it up, and it has a little hologram of the Death Star. Pretty cool. But lots of Star Wars enthusiasm today for sure. But let's get into the actual content now. As we take a look at IP version 4 addressing, we've got to understand the format before we start doing anything with it. And a lot of this is going to be reviewed for you, but you cannot do the fundamentals too many times. We really got to know the fundamentals to understand how to go to the next step. So let's just review a little bit. When we talk about an IP version 4 address on a network, the metaphor I often give my students is it's a lot like a street. Let's say that we have Main Street and we have some houses on Main Street. And these houses each have their own house number. We might have, for example, let's say we've got 101 Main Street, 103, 105, 107. You see, they all have the street in common. They're all on Main Street, but they have a unique house number. Well, it's the same way with network addressing. We're going to have a network address that might look something like this. I might say the network address of the server is 192.168.100.55/24. Well, what we're saying there is a portion of that address refers to, if you will, the street, the network segment that everybody is sharing on that network. So we could say these 4 computers instead of 4 homes, they all live on the same network, like they're living on the same street. They share that part of the address in common, but they have a unique portion of the address for their host. Just like 101 Main Street is different from 103 Main Street, a portion of that address is going to refer to the device on the network. And that dividing line that says, here's the network portion, and here's the host portion, that dividing line is going to be determined by that /24. That's called our subnet mask. Now remember, and you might want to take some notes on this if this is new to you or if it's been a while, an IP version 4 address has 32 bits in it, 32 ones and zeros. And if I say the subnet mask is /24, what that means is the first 24 of those bits refers to the network, analogous to the street. How many's left? 32 minus 24. 8 bits are left. That means 8 bits are going to refer to, the 8 bits are going to refer to the host itself. And to understand and to do some manipulation with this, to alter from the defaults at all, we really need to understand binary numbering. So that's where we're going to start today. And when we talk about binary numbering, we're dealing with a base 2 numbering system, ones and zeros. And this is what a typical IP version 4 address might look like. We've got 10.1.2.3. Here's what I want you to notice. We've got these 4 decimal numbers, and they're separated by a dot. And here's a term for your notes. This is dotted decimal notation. Dotted decimal notation, because we have decimals and they're separated by dots. And what we need to do before today is over is learn how to take each of those decimals, the 10, the 1, the 2, the 3, and convert those into their binary equivalent. Because decimal, that's a base 10 numbering system. We want to convert those into binary, a base 2 numbering system. And we haven't said how to do it yet. That's coming up shortly. But shortly, you're going to know how 10 suddenly translates into 000011010. And here's a huge point I want you to understand. Each of those decimals, they're made up of 8 bits. 8 ones and zeros. Not 9, not 10, 8. And we'll see later that the biggest decimal number you can make with 8 binary bits for your notes is 255. So the absolute biggest number we could have for one of these decimals is 255. That's if all of the binary bits were ones. Now here, you notice I've subdivided this into 4 different areas that I've called octet 1, octet 2, octet 3, and octet 4. Octo meaning 8. We have 8 binary bits in each of these decimal values. And we're going to be referring to that a lot in our calculation. We're going to say, oh, we're dealing with the 3rd octet, or we're dealing with the 4th octet. I want you to understand what that means. It's that 1st, 2nd, 3rd, or 4th decimal number. And the first thing I want us to do is to learn how to take an 8-bit binary number and convert to decimal. And by the way, I see that we've got plenty of questions coming in on our different platforms, and we've got literally hundreds of people watching right now. And I don't want you to think I'm ignoring you. We will have, I think, 4 different Q&A breaks throughout today's session. So if you want to chat amongst some of these like-minded professionals you're in there with right now, feel free. But if you've got a question for me, please save that, if you would, for the Q&A period, because I probably won't see it right now. I'm not ignoring you. But how do we convert a binary number to decimal? Well, let's take the binary number of 100101110. And this is super simple to convert to decimal. Notice I've put this in a table. We start at the we start on the right-hand side with a 1, and then we just double it. 1 doubled is 2, 2 doubled is 4, then 8, 16, 32, 64, 128. And grand total, I have 8 columns because it's an octet. We have 8 bits. So I create this table. In fact, if you're going into an exam environment and they give you one of those dry erase boards to work on, this is something that I almost always do if I'm going to be dealing with binary. Before the exam even starts, before I even click go, I take my little dry erase board and I draw out 128, 64, 30. I do the 8 columns, and I use that for my calculations during the exam. But this little table is going to be super, super handy. Remember, we just start at 1 on the right, and we just double it until we have 8 columns. And what we need to do to convert this binary number into decimal is simply put those 8 bits in those 8 columns. And here's the key. Every time we have a 1 in a column, we just add up that column heading. So I have a 1 under 128. I've got a 1 under 16. I've got a 1 under 4 and under 2. Just add them up. 128 plus 16 plus 4 plus 2 is 150. How easy was that? We just put those 8 bits in a table, and we just added up all the column headings that had a 1 in them. Pretty simple. So we could very easily take an 8-bit binary number and convert it to decimal. There's a little extra work going the other way, but it's still simple. It just takes a little bit longer. Let's go in the other direction. Let's take a decimal number and convert it to binary. We're still going to use that same table that we have. And let's say that we have this number of 167. And we want to calculate the corresponding binary number for that. Well, here's what we do. We're going to, using that table, we're going to take the number we're working with. We're going to start at the left-hand side. We're going to start at the 128 column, and we're going to ask this question. You might want to put it in your notes. We're going to say, is this number I'm working with, which is right now 167, is it greater than or equal to this column heading? Is it greater than or equal to 128? And here's the key. If the answer is yes, and in this case, yes, 167 is greater than 128. If the answer is yes, we're going to put a 1 in that column. And then we're going to find the difference. What is the difference between 167 and 128? Well, 167 minus 128, after we put a 1 in that column, we're going to subtract 128 from 167, and that's going to give us a number of 39. So now we're dealing with a number of 39, and we move to the next column. And we ask the same question for the 64 column. Is 39 equal to or greater than 64? No, it's not. If the answer is no, we're going to put a 0 in that column. And when we put a 0 in that column, let me let me fast forward to where we're actually putting a 0 in that column. We're going to put a 0 in that column and nothing has changed. So we're just going to move along. We're still dealing with the number of 39. And we say, is 39 greater than or equal to 32? Yes, it is. And if the answer is yes, remember what we're doing? We're putting a 1 in that column and we're going to find the difference. And the difference between 32 and 39 is 7. So now we're dealing with a number of 7. And we go to the 16 column. And you're getting it by now, I hope. Is 7 greater than or equal to 16? No, it's not. So what do we do if the answer is no? We're going to put a 0 in that column and move along. Is 7 greater than or equal to 8? Not quite. No, it's still a no. So we're still going to put a 0 in that column. And we're going to move along to the 4 column. Is 7 greater than or equal to 4? You bet it is. So we're going to put a 1 in that column because the answer is yes. And we're going to find the difference. What is 7 minus 4? It's 3. Now we're dealing with a 3. And we go to the next column. Is 3 greater than or equal to 2? It sure is. And because 3 is greater than or equal to 2, we're going to put a 1 in that column. We're going to find the difference. And the difference is 3 minus 2 is 1. So now we're dealing with a 1. And we go to our final column. Is 1 greater than or equal to 1? It's equal to 1. Because it's equal to 1, the answer is yes. We're going to put a 1 in that column. And there is no difference at this point. So we are done. That is the result. We have converted the decimal number of 167 to 101,00111. That's how we go from binary to decimal and from decimal to binary. Now, I've got some practice exercises for you. Now, these are not the pop quizzes that we're doing for prizes. So no prizes awarded for this. This is strictly for practice. But I want you to tell me, and yes, I realize that you could be using a scientific calculator. You could be asking ChatGPT to tell you the answers to some of this probably. Please don't cheat yourself. Go ahead and just work it out on paper. Make sure you know how to go through the steps. So the question I have for you is this, and I'm even giving you the table as a reference so you can jot that down on your piece of paper. But the question I have for you, and go ahead and chat it in when you get it ready or when you're done. My question is, given the binary number of 011,01011, give me the corresponding decimal number if you would. And go. Go ahead and chat it in when you're done. And by the way, there's about a 15 to 20 second delay from the time I say something to the time you hear it. So I might say, hey, nobody's responded yet. And actually they have, but we're just in that 15 to 20 second delay. So give me the corresponding decimal number if you would. I'm looking on all of our different platforms. Wow. I'm getting an overwhelming number of people saying it's 107. Well, let's go through it together. If we just put each of those decimal digits or each of those binary bits in those columns, we've populated 64, 32, 8, 2, 1. Let's add them up. What is 64 plus 32 plus 8 plus 2 plus 1? Yeah, excellent job I was going to read them off, but literally it's flowing off my screen. So many people got the right answer right there. This is going to be a problem when it comes time to give the prizes away. It's going to be hard for me to see who's first in. But let me give you another exercise. Let's go in the other direction. This might take you a couple of seconds longer. Here we're going to go from a decimal number of 49, and my challenge for you is give me the corresponding binary number as I take a sip from my imperial mug here. What is the binary equivalent of 49? Starting to get some answers in now. And most of them are agreeing with one another, so that's excellent. Yeah, I think most people are on the right track here. Let's check it for ourselves. We're just going to go through that series of questions, and I'll do it quicker than I did before when I was explaining it for the first time. But we start with 49 at the 128 column. Is 49 greater than or equal to 128? No, 0, move along. Is 49 greater than or equal to 64? No, put a 0, move along. Is 49 greater than or equal to 32? Yes, put a 1, find the difference. The difference is 17. Now we're dealing with a number of 17. So we put a 1 in the 32 column, and we take our 17 and we say, is 17 greater than or equal to 16? Yes, it is. So we put a 1 in that column and find the difference. The difference is 1. Now, you could, at this point, continue on with that series of questions. You could say, is 1 greater than or equal to 8, to 4, to 2? But you might make a leap in logic right now and realize you've only got a 1. The answer is going to be no for those next 3 columns. So you might just make a logical shortcut right now and say, you know what, I can put zeros in those columns because obviously they're greater than 1. So I could put zeros in 8, 4, 2, and then finally I get to column 1. Is 1 greater than or equal to 1? Yeah, it's equal to 1. So we put a 1 in that column. And I'm agreeing with pretty much all of our students right now, saying it was 0011, 0001. All right, it is time for pop quiz number 1. And I said everything was Star Wars themed today because if you're watching this on replay, and yes, there is going to be a replay, this is the closest thing I could find to a moisture evaporator when I was at Galaxy's Edge down in Hollywood Studios in Walt Disney World in Florida a while back. And it reminded me, in fact, I was there just a few weeks ago, and I was thinking, Star Wars Day is coming up. I'd love to do another, just like we did last year, I'd love to do some sort of live event to celebrate Star Wars Day. And it occurred to me that I could do something on binary. I remember that whole conversation between, remember in episode 4 with Uncle Owen and C-3PO, and I might misquote this, but it goes something like this. Uncle Owen is looking at C-3PO and he says, what I really need is a droid that understands the binary language of moisture evaporators. And C-3PO says, evaporators, my first job was programming binary load lifters. It's very similar to your evaporators in most respects. It went something like that. I thought we could do binary. So here is something that's sort of kind of looks like a moisture evaporator. Now, because I don't want people just using their calculator or using ChatGPT, I'm going to ask you for some extra information. And again, the answers are flying in fast and furious. So I'll tell you, the winner is going to be whichever answer that I see first. I apologize if you came in and I didn't see you, but the winner is going to be whoever I can spot first that gave a satisfactory answer. They're answering all the parts. For example, if I say, translate this binary number into decimal, I don't want you to just say that 110000. I don't want you to say, oh, it's 192. Now, I want you to tell me why it's 192. I want you to say it's 192 because 128 plus 64, those columns that have ones in them, that adds to 192. Show me your work. Don't just give me the answer. That's going to be a requirement for you. So here is your scenario. Moisture evaporators, as we know, use the binary language. And we've got one moisture evaporator on our moisture farm that's reporting an error code in binary. But we've got our moisture evaporator all-in-one repair guide in front of us, and all the error codes, they're in decimal. So we have to translate this binary number into decimal to repair this moisture evaporator. Okay, are you ready? I want you to, again, show me your work. Don't just give me a number. Say, it's this number because these specific columns add up to this number. And the number I want you to translate to translate to decimal is, are you ready? It is, and go. 01011011. Job. I hope you felt like that was fun. Now let's just go through and see why David was correct. What David did was what I'm assuming David did is he took this 8-column table and he put the binary bits into that table and just added up the column headings for all the columns that had a 1 in them. 64 plus 16 plus 8 plus 2 plus 1, that equals 91. Excellent job. Now, I said I would give about 4 Q&A breaks because I realize some of this can be a little taxing if you're not mathematically inclined. And I want to take plenty of breaks. So if you've got questions for me, go ahead and start chatting those in. Again, I'm going to be looking at the live room because I'm going to miss stuff if I try to bounce between 4 different environments. So if you're in the live room and you have a question for me, here's what I want you to do. Preface your question with the few stars, asterisks. That way I know it's a question for me. It's not something you're just chatting with somebody else about in the room. So preface your question with a few little stars. And yeah, we might be able to take a few questions here. While you're doing that, I've got a huge announcement, and so many people that I haven't publicly announced this yet. You're the first to hear it publicly. I sent out a couple of emails to my email list, and people have been super stoked about it, and I think you will be too. You might have heard that last December, Cisco made this big announcement about how they're going to be updating their courses coming up, and they've already started that. They've already come out with a new blueprint for things like CO Core and Encore and NARCI and CCNAs coming up. They're pretty much updating the blueprint to all of their exams, and the thing that just blew me away was they said they're going to be making updates every year. I thought, are you kidding? Every year? They said it'll be small updates. They said less than 20%. But I thought, you know what? This does not fit with my business model. I was thinking that typically I charge $399 for a course because, you know, our courses, they're not 70 hours long. We give you everything you need in less than 20 hours typically. You know, that we simplify everything. So you have good assurance that if you take one of our courses, then you're dramatically increasing your odds of passing the exam. But a challenge now is I don't want to create a new course and expect somebody to buy a course for $399 and it's only good for a year. That doesn't seem fair to you. And I know some people struggle with which course should I go with next, and they kind of hesitate and they have to save up to get this course. You know what I decided to do? I thought, okay, I'm going to make everything super accessible. I want to make it easy and quick for you to just get right into that next course. So and I've had requests for this for a long time, but when Cisco came out with that announcement, I thought, okay, it finally makes sense. We have now launched an all access pass. And in that all access pass, you're going to be able to get streaming access to all of the courses that are currently in our library. I think there's over 25 of them now. And I'll give you a list of what's in there now in just a second. But something else that a lot of people want, they say, well, when are you going to be coming out with this course? And yeah, let me know when this course is released. Well, we're doing so much development this year. Like right now, I've got an AWS Certified Cloud Practitioner course that I've started. I'm also deeply involved in developing the CCS, the Cisco's new one, the CCST networking course. We're dividing that into 4 parts. I've already done the first 2 parts. Part 3 is in the works. Here's the cool thing. You don't have to wait for me to get done. As part of this all access pass, you get streaming access to what I've already done. You get access to like a pre-release version of the course. So you get immediate access. You get a wide selection of things. It's just going to simplify things for you, and it's going to speed things up. And it's less than $1 a day. I'm not asking you to pay $399 for one course. I'm asking you for less than $1 a day, you get access to everything. So $29 a month. $29 a month, you get access to over 25 courses. There's no way you're going to get done with those, by the way, in a year. But you've got a collection. You don't have to decide, should I do this or should I do this? You don't want to make an investment. You got them all. Just taste test them. Pick what's right for you and go for it. So it's going to dramatically speed up your certification pursuits. And for people that have been with me for a while and have a level of trust with me, if you've been with me for maybe a year or 2 or 10, then you might say, you know what? Yeah, that's awesome. I'm in. And for people that want to go ahead and join for an entire year, I'll give you 2 months free. So $290, less than less than the price of one course. You get access to everything for a year. So your choice. Here's what's in the library right now, the All Access Library. You see that brand new, you cannot even buy this individually from me right now. It's just part of the library. Parts 1 and 2 of CCST Networking, which is panning out to be the best course I've ever done. I'm really geeking out with some of the animations and some of the new teaching things in a new way. It's the first course where I'm going to be teaching Wireshark, and there's some cool new topics in there. Also, my AWS Certified Cloud Practitioner, that's in the pre-release stage right now. There's still more to do, but I've already got 2 or 3 modules done in that. As well as our flagship courses. You get CCNA and Encore and CO Core and Security Core and Service Provider Core and just all this stuff. You can read through it if you want. Here's how you get it. No discounts or anything because it's already crazy low priced. Well, the discount is sign up for a year. 2 months free. But just go to kwtrain.com/all-access. There has been so much enthusiasm around this from the people I've already introduced it to. And you're the first to hear about it publicly. So you might want to go ahead and jump on that and just start watching stuff right away. You don't have to choose, or you don't have to make a big financial commitment and choose one. Just kind of sample what you want and go for it because you got access to everything. So let's march on, shall we? Now that we know how to go back and forth between binary and decimal, let's get back to our discussion of IP version 4 and take a look at its format because this is going to be critical in our calculations. We looked earlier at a sample IP version 4 address, something like 10.1.2.3. And we said that each of those decimals represented an octet. So 10 is an octet 1, 1 is an octet 2, 2 is an octet 3, 3 is an octet 4. And we said we're going to be able to take a 10 and convert it into binary. And you know how to do that now, don't you? You can convert a 10 into binary. It's going to be 4 zeros, 1 0, 1 0. I think if I'm doing that right from memory. Oh, and it is. I forgot I had the answers there. And if we look at those 32 bits in a row, we've got that paradoxical question that we started off with. If I'm looking at this number, how do I know which part refers to the network or the street, metaphorically, and which part refers to the host? We have to have a dividing line that says everything on this side, that's the street or that's the network. Everything on this side, that's the host or the house number. And the thing that draws that dividing line is our subnet mask. Here's what I want you to know about a subnet mask. You might want to put this one in your notes. I was wanting to make a statement. I want to make sure it was true in every case, and it pretty much is. So a subnet mask is going to be okay. You can have a subnet mask of all ones. You can't have a subnet mask of all zeros. But in general, a subnet mask is going to be a series of ones, contiguous ones, followed by a series of zeros. You're not going to have a subnet mask of 1 1 0 0 1 1 0. No, bunch of ones, bunch of zeros. Now, here's the key. Here's how you interpret that. Every time you have a 1 in your subnet mask, the corresponding bit position in your IP address, that's a network. That's part of the network address. So here I've got 8 ones and 24 zeros. That means the first 8 bits in this address refer to the network. The last 24 bits refer to the host on that network. So I have, in this case, 8 network bits, and then I have 24 host bits. So if somebody says, hey, what's your IP address? I could say, oh, it's 10.1.2.3. If I do that and don't give them any subnet mask information, that has some value. I mean, after all, they could ping it, but that's not enough information to know what network I'm on. So we need to be a bit more specific. there's a couple ways we might write this. We could say, my address is 10.1.2.3/8. If you see /8, the 8 means there are 8 network bits. We have 8 ones in the subnet mask. For your notes, sometimes that's called slash notation or CIDR, CIDR, classless interdomain routing, CIDR notation. Another way to write that is to put our subnet mask in dotted decimal. This is very common. You have to use this syntax a lot of times in Cisco iOS when you're doing your configurations. Well, you could say it's 10.1.2.3 and the subnet mask is 255.0.0.0. Because if you take 8, this is a big deal. You got to know this. If you have 8 binary ones, in decimal, that's a 255. If you add it up, 128 and 64 and 32 and 16 and 8 and 4 and 2 and 1, that's 255. So let's say you had 24 ones in your subnet mask. That would be a subnet mask of 255.255.255.0. So we could write it as a slash notation or in dotted decimal. And this is one of the most important things to learn today, because when we do our calculations later on, when we're doing our design calculations later today, and somebody asked how long today is going to run, my guess is between 2 and 3 hours. Definitely not more than 3 hours, probably a little over 2 is just a guess. But I need you to know these different classes of addresses. Class A, B, C, D, and E. You can tell the class of an address just by looking at the first octet. If the first octet has a value in the range of 1 through 126, it's a class A. And here's the thing I need you to know. When classes A, B, and C, they have a default subnet mask. So if we don't mess with it, I need you to know what it is by default. If you're dealing with a class A network, then its subnet mask by default is 255.0.0.0. So in slash notation or prefix notation or CIDR notation, however you want to say that, it's a /8. That's if our first octet is in the range of 1 through 126. By the way, you might wonder, why didn't we start at 0? 0 is used for something else. When we get into, for example, I don't want to get into DHCP today, but when a host comes up on a network, it doesn't have an IP address. And it sends out this broadcast trying to locate a DHCP server to get an IP address. And you might wonder, if it doesn't have an IP address, what is its source IP address at that time if we were to look at the packet? It's all 0. So we cannot use a 0 as our first octet. But we can use 1 through 126, and then we go to 128 through 191. That's a class B. Its default subnet mask has 16 bits in it. It's 255.255.0.0. And you might wonder, didn't we skip one? What happened to 127? 127, specifically 127.0.0.1, that has a very special mission. That's called our loopback address. That is an address that refers to your own device. If you were to go out into a console on your operating system right now, probably, and you said ping 127.0.0.1, it should work. You should get ping replies because you're talking to your local network interface card. It's a great troubleshooting thing. Or some web developers. They'll have a web server running on their machine and they'll point their browser to 127.0.0.1 because it points back. It loops back to their machine. Class C networks, they begin with 192 through 223. They have a 24-bit subnet mask by default. Now, these are the addresses that we would assign to a host or a network device. Only classes A, B, and C. I need you to know, for the real world, for any exams you're going to be taking, I need you to know the range of values in the first octet and what their default subnet mask is. And here's a common point of confusion I've seen so many people fall into. A lot of people will say, I I've got this address of 10.1.1.1, and yeah, I know by default it's a class A network and it has a /8 subnet mask, but I've given it a /24 subnet mask. So now it's class C, isn't it? No, please hear me on this. The subnet mask has nothing to do with the class of address. I don't care what subnet mask you assign, you can completely identify the class of an address just by looking at the first octet. It doesn't have anything to do with the subnet mask. It's just the value in the first octet. You can change the default subnet mask. Doesn't change the class of address, though. Let's take a look at class D now. In class D, our values are in the range of 224 through 239. And it's not really meaningful to say that they have a subnet mask because this is not an address that we're going to be assigning to a host. This is going to be used for multicast. What is multicast? Well, let's say that I wanted to send out traffic to 100 different recipients, a video stream perhaps. I don't want to send them individual streams. That's going to take up a lot of bandwidth. If I do that, what did I say, 1,000 or 100, a bunch of recipients. With multicast, I can send it one time, and it's going to go to all members of a multicast group. So we could have this group that was numbered 224.50.1.2, just to make something up. And a device that wants to receive that stream, they could join that group. And all members of the group are going to get it. But I only have to send it one time. So these IP addresses in Class D, they're really multicast group addresses. By the way, if you want to learn a lot more about multicast groups, not really the topic of today's discussion, but just go to YouTube and search for Kevin Wallace multicast. And I've got I think it's about a 45-minute video, one of my more popular videos, where we get into what multicast is, how it operates, all the different terminology. We show you how to set it up and how to configure it, how to verify and troubleshoot it. But that's a multicast address. Now, finally, there's a Class E address. I predict that you will never, ever see one of these. I've been studying networking since the early 1990s, well, 1989 to be specific. And I've heard for decades now that Class E is used for, quote unquote, experimental. I'm sorry, I hate air quotes. I just did that. My apologies. It's used for experimental purposes. I've never seen such an experiment. I doubt that you will either. I have heard of one person that say they used it for something, but I've never needed, and I doubt that you'll ever need a Class E. But it's important to memorize again the first octet ranges for classes A, B, and C and their default subnet masks. There are also some IP version 4 addresses that cannot be routed on the public internet. It's important to know those as well. And the interesting thing about IP version 4 addresses is we're out, to be honest. You cannot go to your country's numbering authority and say, hey, I'd like a class B block of addresses, please. They'll say, no, we don't have any. We're out. So the question is, how do we keep adding networks if we're out of addresses? Well, here's the thing. Within our homes, within our businesses, we can use private IP address space. Like the 10 dot address space. If we have an address that begins with a 10, that cannot be routed on the public internet, but it can be routed within your company. And remember that a 10, Class A has a default subnet mask of 255.0.0.0. Class B, in my home, I use the 172.16 network, and I have it I may or may not have it subnetted. I'm having trouble remembering how I set that up. But everything begins with 172.16. Well, that cannot be routed on the public internet, but it can be routed inside of my home, and that's Class B, and it has a default subnet mask of 255.255.0.0. Now, here's an odd one. Here is another address that cannot be routed on the internet. If it begins with 169.254, that cannot be routed on the public internet, nor can it be routed on your network. It cannot pass through a router. This is a special type of address called an APIPA address. That stands for Automatic Private IP Addressing. You might see this. Let's say you plug in a Windows laptop. It tries to go out and find a DHCP server to get an IP address, but it fails. It couldn't find one. It will self-assign it an APIPA address. You say, what is the IP address of this laptop? If it starts with 169.254, that's probably an issue. It was unable to obtain an IP address, and you didn't statically configure one. So that's a nearly useless address. I mean, if you had two devices on the same segment and they had their own APIPA addresses, yeah, technically they could communicate, but this isn't routable at all. We also have a private IP address space for Class C. It begins with 192.168. And again, Class C, it's got a /24 default subnet mask. So just a review of some of the different characteristics of IP version 4. Now, let's get to the main topic today, which is subnetting. We needed to know about binary numbering. We needed to know about the structure of an IP version 4 address. Now, let's talk about what subnetting is, and we're actually going to do some. Let's say that we had an office space like this. You've got this floor of a building. Maybe it's the same company, but we've got these different departments. We've got executive offices. We've got a public, not a public, but we've got a training room. We've got presentation rooms. We've got maybe a call center. We've got all these different distinct functions. Well, we might want those to be in separate networks, in separate subnets, because maybe there's a printer in the conference room. If I'm in the call center and I say search the network for printers, it can find that printer in the conference room or in the training room if it sends out a broadcast, because a broadcast goes throughout a subnet. So what do? We can take our address. Let's say that we've been given the address space of 192.168.1.0/24, and we said, all right, here's the address for this entire floor, all of these offices. Well, I don't want to use just that one network. I want to break it into, let's see, 1, 2, 3, 4, 5. I think we got about 7 different areas where I'd like each of them to have their own subnet. So what we can do is give each of those areas their own network address space, their own subnet, their own broadcast domain, because a broadcast does not go out of a subnet. In order to get from one subnet to another subnet, we've got to route. So for security reasons, for performance reasons, we would want to separate these into different subnets. Now, what we're going to learn to do is to take that default subnet mask, which I said was /24, and we're going, here's a key term that you got to know coming out of today's session. We're going to add some bits to the default subnet mask, and that's going to break that one network into 7 networks. Or actually, you can break it into 8 networks. Here's the thing, though. It's called borrowed bits. We, by default, because it's a Class C network, by default, we had 24 bits in our subnet mask. Well, I added 3 bits to give me a 27-bit subnet mask. Here's the definition for your notes. The number of let me rephrase. Borrowed bits are the bits that you add on to the default subnet mask. So this is where it's super important to know, are you dealing with a Class B network? Or are you dealing with a Class C network? Because they have different default subnet masks. If I were to say, yeah, I'm using 3 borrowed bits. Well, I don't know if I'm dealing with a /19 subnet mask or a /27 subnet mask, because I'm adding them on to the default, to the classical, to the natural subnet mask. So I have to look at this and say 192 Class C. It defaults to 24 bits in the subnet mask. Okay, I borrowed 3 bits. 24 plus 3 is 27. So you got to know what class you're dealing with and what the default subnet mask is for that class in order to know what 3 borrowed bits look like. But the borrowed bits, that's what we add on to the default subnet mask. And another reason we might want to subnet our network is to avoid wasting address addresses. If I used the default subnet mask for 192.0.2.0/24 and I wanted to interconnect two of my buildings, I've got R1 at one side, I've got R2 at the other side. How many IP addresses do I really need on that network segment? 2. R1 needs an address, R2 needs an address. That means I have just wasted 252 addresses. I burned an entire subnet for 2 addresses. So this would have been a great opportunity for me to use some borrowed bits. I could have added bits and I could have had a /30 subnet mask. That would have given me my 2 usable addresses. So I just wasted 252 addresses by doing that. And that was with the Class C network because it only has 254 usable addresses to start with. Class A has over 16 million addresses by default if we use the default subnet mask. Class B has over 65,000. So one reason that we want to do subnetting, don't waste addresses. Another reason we might want to alter the subnet mask is to do network summarization. Maybe we are a service provider or we're dealing with a large enterprise network with lots of routes. Instead of maintaining all of these individual routes in my routing table, instead of, just to keep it simple, I know four networks is not a lot, but just as an example, instead of sending out 4 separate advertisements to my neighbor, what I could do is I could look at these 4 networks that I'm trying to advertise and I could say, they have a lot in common. They all start with 192, so their first 8 bits are all the same. The second octet, those are all 168, so the second octet, they're all the same. But then I've got different numbers in octet 3. I've got 1 and 14 and 25 and 30. But once I break that down into binary, you look at octet 3, can you see that within octet 3, each of these 4 networks still have the first 3 bits in common in octet 3. So grand total, 8 plus 8 plus 3. We got 19 bits in common among these 4 different subnets. So instead of sending 4 different advertisements, what if I did this? What if I advertised just one network with a /19 subnet mask? Here's what that would look like. If I had a subnet mask with 19 bits in it, and I say the first 19 bits represent the network, in decimal, what would that look like? Well, all ones is 255. So we've got 255.255. And then in that third octet, I've got 111 and then 5 zeros. What is 111? Well, it's 128 plus 64 plus 32. That's 224. So now I've got a subnet mask of 255.255.224.0. Now, there are 2 addresses within a network I need you to understand. There's the address of what sometimes people call it the address of the wire, the address of the network itself, and there's something called a directed broadcast address. If I send a directed broadcast address into a subnet, it goes to everybody within that subnet. And in this case, the network address is going to be where we have all of the, for your notes, the network address is where we set all of the host bits to zeros. So I'm going to bring down all these bits that we have in common. I'm going to set let's say we've got 19 network bits. That means we have 13 host bits. I'm going to set those 13 host bits to zeros. And this is what it looks like in binary. If I convert that to decimal, then I've got a network address of 192.68.0.0. What is my directed broadcast address that goes everywhere within that subnet? Well, we have to set our host bits to 1. We've got 13 of them. So I'm going to set my 13 host bits to all 1s. And I bring down those 19 bits in common and then add on 13 1s. This is what it looks like in binary. If we do the conversion, that comes out to be 192.168.31.0. 25.255. That's the directed broadcast. So when we say we're dealing with this network, and by the way, we can now advertise. We could advertise 192.168.0.0/19, and that is going to encompass all four of those networks. So if somebody wanted to go to an IP address on one of those subnets, we've got this summary route that includes that address, and we know how to forward it on. Now, what I just did was demonstrate something called supernetting. Supernetting is when I don't add bits to the default subnet mask. I removed bits from the default subnet mask. So you see, the default subnet mask was /24. Well, I removed some of those bits and I made it a /19, I think it was. That's supernetting. That allows us to do summarization. Or we could add bits to the default subnet mask. That's called subnetting. That allows us to take one network address space and chop it up and add bits to it. Now let's get mathematical. Let's get into our design process finally. We want to be able to calculate the number of subnets that we would create given a certain scenario, given a certain number of borrowed bits. Here's the formula for your notes. If you want to add bits, if you want to borrow bits and add those on to your default subnet mask, you're going to create this many subnets. The number of created subnets is 2 to the power of s, where s is the number of borrowed bits, the bits that we have added on. Let's give you an example. Let's say that I've got a subnet mask of 255.255.224, and I've applied that to a class C network of 192.168.1.0. And just as a reminder, I'm putting the /24 to remind us that's the default subnet mask for class C. Well, how many bits did I borrow? Well, I started with 24 bits. I started with 225.225.225.0, but now in that fourth octet, I've got 224, don't I? How many bits? You tell me, put it in the chat. How many bits do you think I had to borrow to come up with a 224 in that octet? Go ahead and chat that in if you would. Yeah, I'm already seeing the first answer come in. It's had to borrow 3 bits. And we want to ask how many subnets just got created. Well, we need to know what class of network we're dealing with. Here, I told you that it was a class C network, and I told you what the default subnet mask is. But in the real world, maybe you have a network of 172.16.1.0, and you think, okay, I just applied a /27 subnet mask. How many borrowed bits? Well, if I were dealing with a class B network, and I applied a /27 subnet mask, then I just borrowed, let's see, 16 to 27. I just borrowed 11 bits. That's going to give me a very different answer than for a class C network. This is why I was saying it's so critical to understand what class of address we're dealing with and what its default subnet mask is. But we're dealing with class C because it begins with the 192. We know that its natural or its default subnet mask is a /24. Our subnet mask, we're told, is 255.255.255.224, and many of you are telling me that is going to be 3 borrowed bits. It's a /27. So we've got 3 borrowed bits, and that's going to create 2 raised to the power of 3. It's going to create 8 subnets. We just created 8 subnets by borrowing 3 bits. So if you had a design where you go into a company and you have these 8 different departments, kind of like in that office space I showed you earlier, and you're trying to figure out how to give each of those office spaces their own subnet, you would need to add 3 borrowed bits to chop it up into 8 subnets. Let's take a look at the other big question, which is, okay, once I borrow some bits, how many hosts can I support in that subnet? And the formula is 2 to the power of h minus 2. Now, h is the number of host bits. So in that example we just went through, we had a slash 27. That tells me that we would have 5 host bits because 32 minus 27 is 5. So it would be 2 to the power of 5, which I think is, I think that's 32. And we subtract 2. Now, why are we subtracting 2? Because remember, there are 2 addresses that we cannot assign to a host. We cannot assign the network address where the host bits are zeros. We cannot assign the directed broadcast address where the host bits are ones. So we have to subtract 2 to give us the number of usable addresses. And in this example, we've applied this same subnet mask to this same Class C network. So we're dealing with a slash 27 subnet mask. And now we're asking the question, all right, I chopped this into 8 subnets. How many hosts can I support per subnet? Well, we've got to figure out how many host bits we have. If I've got a slash 27 subnet mask and we've got a 32-bit address, 32 minus 27, I got 5 host bits. It's going to be 32 minus 27, that's 5. What is 2 raised to the power of 5? It's 32, but we got to subtract 2. That's going to give us 30. So we can have 30 hosts per subnet. And remember what we're doing here. We're not including the network address. The network address is where we have made all of the host bits zeros, like I'm showing you here. The network address of 10.1.2.3/8 is 10.0.0.0 because I've made those 24 host bits all zeros. We also cannot use the directed broadcast address. That's where we take those host bits and we convert those into all ones. So here I've got 24 host bits with 10.1.2.3/8. So I keep my original 0.0.0.0.10.10. That's a 10, but then I set all the host bits to 1. So that's going to give me a directed broadcast for this network that you see on screen of 10.255.255.255.255. Now, let's do a practice exercise. Now, again, this is not for points. This is not for a prize. This is just for our own practice. But I'd still love for you to type in the answer. Yeah, well, actually, let's do this one together. I'll let you do the next one on your own. Let's do this one together. Here's our design exercise. Let's say that your company has been assigned a network of 172.20.0.0/16 for use at one of its sites. Now, here is your design requirement. You need to accommodate 47 subnets at that site. And when you do that, you don't want to just add a whole bunch of host bits that gives you maybe 1,000 subnets. You need to meet the design requirement of supporting at least 47 subnets while maximizing the number of hosts that you can have per subnet. Now, what that means is don't use more borrowed bits than you need to give you 47 subnets. Because if you keep adding borrowed bits, that cuts down on the number of hosts you can have. So here's how we could approach this. We can write out our table. Remember the formula that we had? It was 2 raised to the power of s, where s is the number of borrowed bits. We could write out a little table on our dry erase board in the exam environment. And let's just look at the powers of 2. 2 raised to the power of 0, well, anything raised to the power of 0 is a 1. So if I don't borrow any bits, I've got that one network. If I borrow 1 bit, 2 raised to the power of 1 is 2. So I'd have 2 networks. So we keep doing this. Now, our goal is 47 subnets. And as I look through there, I'm kind of zooming in on 5 borrowed bits and 6 borrowed bits. 5's not quite enough. If I borrowed 5 bits, that would give me 32 subnets. Not quite enough. But if I borrowed 6 bits, that gives me 64. That's too much. What do I do? Well, you cannot borrow 5.5 bits, so you have to go with the minimum number that still meets the criterion. So even though it's more than we need, 6 is the minimum number of borrowed bits that we can select and still get 47 subnets. So we say, I need 47 subnets, 5 borrowed bits, not quite enough, 6 borrowed bits, a little bit more than enough, but I got to go with 6 because that's still the minimum number of bits that will give me my result. And if I have 6 borrowed bits, and I think I'm dealing with a class B network because the first octet is 172, and I know that a class B network by default has 16 bits in its subnet mask. Well, if I add 6 bits onto 16, it's going to give me a /22. So the answer is I would apply a /22 subnet mask, which in decimal would be, dotted decimal would be 255.255.252.0. And at some point, hopefully you'll get to the point where you can just look at a number and know what it translates back into in decimal. But if you need to work it out, you could just say, all right, what is 128 plus 64 plus 32 plus 16 plus 8 plus 4, and that adds up to 252. All right. Let me have you do this one on your own. Again, this one's not for a prize. This is just for your practice. And my challenge for you is a little bit kind of going in the opposite direction. We're still dealing with the same network of 172.20.0.0/16. Here's your goal this time. You're not so concerned about the number of subnets. You're concerned with the number of hosts that you can support per subnet. You need to accommodate 100 hosts per subnet. But don't just borrow like a couple of bits and you support like tens of thousands of hosts per subnet. You need to support at least 100, but you don't want to do that at the expense of giving up subnets. So I want you to maximize the number of subnets that you can have while still meeting this criterion of supporting 100 hosts per subnet. So don't use more host bits than you need. All right. Go ahead and get started, and hopefully within about a minute or so, we'll have some people coming in with correct answers. So go ahead. Again, not for prizes this time. This is just for practice. Well, I'll be looking for that to come in. Already getting some answers coming in. A lot of people are saying that we should use a 25-bit subnet mask. I'm seeing a 23. I'm seeing another 23. We're kind of split. About half of the people are saying 23. About half the people are saying 25. Okay, let's go through it together. Again, we got to support 100 hosts. Let's make our table, this time using the formula for hosts. It's 2 to the power of h minus 2. H is not the number of borrowed bits. H is the number of host bits. Well, and 2 to the power of 2 is 4, but we got to subtract 2 from that because we cannot use the network address. We cannot use the directed broadcast address. So if I borrowed 2 bits, if I had 2 host bits, that would give me 2 networks. If I had 3 host bits, that would give me 8 minus 2, that would give me 6. And we fill out this table. And we need to support 100 hosts. Now, I'm noticing if I had 6 host bits, that would support 62 hosts, but that's not enough. 7 host bits gives me more than enough, but still, 7 is the minimum number of host bits I can have and still meet this requirement of supporting 100 hosts. So if I have 7 host bits, how many network bits do I have? 32 minus 7 is 25, isn't it? So we're going to have a /25. We want to support 100 hosts. We said 6 host bits are not enough. 7 host bits, more than enough, but we got to go with 7. You got to round up. And that tells us that if I've got 7 host bits, I've got 25 network bits. So my subnet mask is going to be a /25, which we could write alternately as 255.255.255.128. Let's take a look at pop quiz number 2. Again, keeping it very Star Wars themed. And these are all pictures I took, by the way, with stuff that I have around here. Yes, I do have a Baby Yoda. And here's the scenario. If you watched Mandalorian Season 3, You notice that, after Bo-Katan and Din Djarin went to Mandalore, they decided that sure enough, it was inhabitable. And now the different Mandalorian clans and houses and groups, a lot of them are coming back to Mandalore to settle. And I looked it up on Wikipedia, and apparently there are 12 of them. We've got 12 Mandalorian clans, we'll call them. And the challenge is we need to give each clan their own subnet. And the network we're working with is 172.16.0.0. And we want to support at least 12 subnets, one for each Mandalorian clan. And we want to maximize the number of subnets. I want you to tell me the subnet mask in dotted decimal notation that will meet this criterion, and tell me the number of borrowed bits. So don't just tell me the subnet mask, tell me how many bits that you borrowed to make that happen. You want to support 12 subnets. Go. We're using the formula that the number of subnets is 2 raised to the power of s, where s is the number of borrowed bits. Well, if I borrowed 3 bits, that would give me 8 subnets. If I borrowed 4 bits, that would give me 16 subnets. Now, I've got 12 Mandalorian clans, so I need to support 12 subnets. 3 borrowed bits is not enough. I've got to go with 4 borrowed bits. And we're dealing with a network that is class B. I got a typo on the screen. My apologies. Obviously, I meant class B there, not class C. 172.16, it's a class B network, not class C, which does have a default subnet mask of 255.255.0.0, which is class C. That is correct for a class B network. That was just a typo where it said class C. So if we're adding 4 bits, that means I've got 4 borrowed bits. I'm adding that to a /16 network. That's going to give me a /20 subnet mask. But I ask you to give me that in dotted decimal notation, 255.255.240.0. Let us now calculate the usable range of IPv4 addresses. This is really the big goal that we were getting through all this. We want to be able to not only say, well, I've created 8 subnets. Now that I've done that, here's subnet 1, here's subnet 2. What addresses do I actually use in those different subnets? And this is one of the most challenging, I'll say. I don't think it's that complicated. It's one of the most challenging topics for a lot of my students. So let's take a look at a super simple example. We're going to make this super simple by doing things at a classful boundary on a dot. So let's say we've got this class B network. Please follow me on this because we're going to build on it. This is no time to be scrolling social media. You got to pay super close attention here. But let's say that we've got this class B address of a network address of 172.25.0.0/16. And I apply a /24 subnet mask. In other words, I borrowed 8 bits. When I did that, let's see, how many subnets did I create? 2 to the power of 8. 2 to the power of 8 is 256, isn't it? So I've created 256 subnets. And I've given you the pattern of those. It starts at 172.25.0.0/24.1.0.2.0 all the way through .255.0. So starting at 0, we just created 256 subnets. Now, how did I know that those were the subnets that I just created? Well, notice that all I did was count by 1 in the third octet. How did I know to do that? Once you understand this, you're going to be able to calculate subnets for anything. So this is one that's easy to visualize. We'll get into one that's not so easy to visualize in a moment. But what we have to do, for your note, please write this down in your notes. I want you to identify 2 different values. I want you to know these 2 different terms. The first term is the interesting octet. The second term is the block size. Once you know that, it's going to be super simple to do your subnetting. So, what is the interesting octet? When you're looking at the subnet mask, it is going to be the last octet to contain a 1. Remember, a subnet mask was a bunch of 1s followed by a bunch of 0s. Well, 255.255.255.0, what is the last octet to contain a 1? It's the third octet. In fact, it's got all 1s. It wouldn't have to have all 1s, but the very, very last 1 in the subnet mask, that's in the third octet. So we're going to say that our interesting octet is octet number 3, our third octet. Now I need to calculate what's called the block size. The block size is, here's the formula, the block size is 256 minus whatever the subnet value is in that interesting octet. So in this super simple example, it was 255.255.255. That's our interesting octet, .0. So the subnet value in the interesting octet was 255. That means my block size is going to be 256 minus, in this case, 255. That's 1. So our block size is going to be 1. Now we know the interesting octet and we know the block size. So here's how we calculate those subnets. Starting at 0, we are going to count by the block size in the interesting octet. That is the most important statement I've made all day. We're going to count by the block size in the interesting octet. So notice in octet number 3, starting at 0, we count by the block size, which is only 1 here. So it was 0, start at 0, then 1, 2, 3, 4, 5, all the way through 255. Once you identify the interesting octet and the block size, it's going to be super simple to identify which 8 subnets did you just create. So remember, for the host or for the network address, all of our host bits are going to be set to a 0. For the directed broadcast address, all of our host bits are going to be set to a 1. So let's take a look at that very first subnet where all the host bits are 0s. The network address is 172.25.0.0. The last 8 bits are host bits. We're going to set those to all, our subnet mask shows us that our last 8 bits are all 0s. And the network address is going to be 172.70 or 25.0.0. Our directed broadcast address is where we make those last 8 bits all 1s. So the directed broadcast is going to be 172.25.0.255. We cannot use those 2 IP addresses to assign to a host. You cannot, please put it in your notes if you didn't already know this. You cannot assign the network address where all host bits are 0s. You cannot assign the directed broadcast address where all host bits are 1. Now, once we've figured that out for what's the network address and what's the directed broadcast address, what is the first assignable address? Well, the first assignable address, technically it's defined as, well, you're going to add a binary 1 to the far, far, far right side of your network address. You're just going to add a binary 1 to it. And when you do that, it's going to give you, in this case, 172.25.0.1. Here's what I would tell you, though. You don't even really have to go through all this binary math. Just add 1. If your network address is 172.25.0.0 and you want to come up with the first usable address, just add 1. That is your first usable address. What is your last usable address? Well, the last usable address is going to be the directed broadcast address. And we subtract a binary 1. So the directed broadcast address, the directed broadcast address, in this case, is going to be 172.25.0.255. We subtract a binary 1 from it, and that gives us 172.25.254. Again, or excuse me, that's the last usable address. Again, you don't have to do the binary. Just take your broadcast address and subtract 1. Basically, the usable addresses, it's this simple, folks. The usable addresses are anything in between the network address and the directed broadcast address. So add 1 to the network, subtract 1 from the directed broadcast. That is your usable range of addresses. And it's going to work out like this. Our subnets are going to be 172.25.0.0. We count by 1 in the interesting octets. And you see they start to list out there. The directed broadcast, you might have to use the binary to figure out your very first directed broadcast, where you set the host bits to a 1 and see what that is. And we did that, and it was 255. But here's the cool thing. Once you find your first directed broadcast address, you don't have to keep doing the binary. You're going to count by the block size in the interesting octet, not just for the network address, but for the directed broadcast address. So you got your first one, 172.25.0.255. Notice, again, we're counting by 1, the block size, in the interesting octet, in the third octet. Now, I think that one was hopefully that was fairly easy to visualize. I wanted to give you one that was easy to visualize so we could see that we're counting by the block size in the interesting octet. Now let me give you a more real-world example, one that's not so clean, but more likely to show up in the real world. Here's our scenario. We want to apply a 26-bit subnet mask to our 192.168.0.0/24 network address space. The question we want to answer is, what subnets did we create when we did that? And what are the usable address ranges in those subnets? Well, looks like I borrowed 2 bits, doesn't it? I have a default subnet mask of /24. I applied /26, 26. I borrowed 2 bits. Well, question 1, always question 1, who is the interesting octet? And if we look at our 26-bit subnet mask, what is the last octet to contain a 1, a binary 1? The 4th octet. The 4th octet is going to be our interesting octet. It's the first non-zero, or excuse me, it's the first, if you looked at it in binary, it would be the last octet to contain a 1. And it's the very last one. So the 4th octet, that is our interesting octet. And the subnet mask is 255.255.255.192. What's the block size? Well, it's going to be 256 minus whatever the subnet value is in the interesting octet. So what is the subnet value in octet 4? 192. What is 256 minus 192? 64. That's our block size. So starting at 0, we're going to start counting by 64 in octet number 4. So right now we set everything to 0 to start with. So it's 192.168.0.0/26, and then we start counting by 64 in the 4th octet. So it's 192.168.0.0.64.0.192.0.190, Now, why didn't I keep going? If I were to add 64 to 192, that would be 256. That's too big of a number. We cannot represent 256 with 8 bits because we start at 0. So those are our subnets. Now, what are the usable ranges for those subnets? Well, we can write our subnets in one column, and we could go through the binary math, and we could write out that 26-bit subnet mask, and we could put 1s in the last 6 bits, which would be columns 32, 16, 8, 4, 2, 1. We could add all those up and say, oh, that's 63. We could do that. That might be easier to visualize when you're getting started. But for me, I'm going to say, I'm just going to look at the next subnet, .64, and I'm going to subtract 1. I mean, these numbers are all contiguous. So if I look at my next subnet, which ends in a .64, I'm just going to subtract 1. And that gives me my directed broadcast address for the previous subnet. How easy is that? So now I've got my subnets. I've got my first directed broadcast address. And remember the shortcut I gave you? I said that once you've got your first directed broadcast address, you can count by the block size in the interesting octet to give you all the other directed broadcast addresses. So starting at 63, I'm going to say 63 plus 64, 127, plus 64, 191, plus 64, 255. And what are the usable ranges of addresses? Anything in between. That's how simple it can be. All right, it is time for pop quiz number 3. Are you ready? Here, we're going to the Death Star. And the control panel for cell block 1138 on the Death Star, it has an IP address of 172.16.25.78/26. So that's the control panel. R2 needs to access that to shut down the garbage compactor. He needs to know the network address of that. So my challenge for you is to tell me what is the network address on which 172.16.25.78/26 resides. But beyond that, I want you to tell me what is the interesting octet and what is the block size. I don't want you to just give me the number. I want you to tell me the network address, the interesting octet, and the block size. Interesting octet with a /26 is the 4th octet. That's the last octet to contain a binary 1. What is the block size? Well, let's see. /26, we've borrowed 2 bits. So that's 128 plus 64, that's 192. I've got a value of 192 in that interesting octet. What is 256 minus 192? 64. So I'm going to be counting by 64 in octet number 4. And it's going to be 172.16.25.0, .25.64, .25.128, .25.192. And the control panel that R2 needs to access ends in a .78. Which one of those subnets does .78 fall in? Yeah, it's somewhere between .64 and .128. So it's in the .64 network. That's how we got the answer. Let's get into our final section today. I said we'd probably go between 2 and 3 hours, so we're right on track to do that. And we did want to, even though we don't really get into the concept of subnetting with, even though you technically can do subnetting with IP version 6, the main thing I want you to do with IP version 6 is understand how the addressing works. So let's talk about IP version 6 addressing. And let's compare it first with IP version 4 addressing. IP version 4 used 32 bits, 32-bit addresses, and like I said, we're out of entire address blocks of addresses where you can just call up your country's numbering authority and say, can I even have a class C? They're just not available. But there are going to be plenty of IPv6 addresses for the rest of our lives. I feel like Bill Gates saying that, 640K is as much as anybody would ever need on a computer. But I'm pretty confident that we're not going to run out of IPv6 addresses in our lifetime, because there are like billions of IP version 6 addresses available for every person on the planet. It's crazy when you look at the math, because it is a whopping 128-bit address. So the great news is we're not going to be running out of addresses. The bad side is, or the downside is, that's a really big address to write out. Do I have to write out 128 bits to work with this stuff? No. In fact, it's even kind of long to write out with decimal. So we're going to use a different numbering system with IP version 6. We're going to use hexadecimal numbering. A hexadecimal number is where we have one digit that could be one of 16 different values. Now with binary, with base 2 numbers, a single digit could be either a 1 or 0. So it could be 2 values. Base 10 numbering, decimal, it could be one of 10 digits, 0 through 9. Hexadecimal could be one of 16 digits, which is 0 through 9. And then when we get to what we would call 10 and decimal, we start using letters. We go A, B, C, D, E, F. So a 10 in decimal, that's going to be an A in hexadecimal. An 11 in decimal, that's going to be a B in decimal. All the way to 15 in decimal, that's going to be an F in hexadecimal. And I'll give you a table that shows you that. But we really don't talk about having network bits necessarily, even though we kind of do. They're called prefix bits. The prefix is the network prefix. These are the bits that represent the network. And we don't talk about a subnet mask length. We talk about a prefix length. But this is analogous to a subnet mask length, honestly. So we've got a prefix that does represent the network. The length, that's the number of bits in the prefix, and the host. Now, I would say that more than half the time, we're just going to take those 128 bits and split it down the middle. The first 64 bits, network. Last 64 bits, host. There are, of course, plenty of exceptions, but most of the time, that's the way it's going to be. And we're going to be dealing with 32 hexadecimal numbers. So even with hex, we still have to write out a bunch of numbers. 32 numbers. Now, a couple of terms for you. The way we're going to write this, it's not going to be in dotted decimal notation. It's going to be in colon hexadecimal notation, I guess we could say. I just made that term up. I've never used that before. But we're going to have hexadecimal. We're going to have a group of 4 hexadecimal digits and a colon. 4 hex digits and a colon. And a group of these 4 hex digits, we're going to call that a quartet. Quartet meaning it contains 4. So a quartet is 8 hexadecimal digits. And one hexadecimal digit, we said it can have one of 16 values. If we were to break that down into binary, how many binary bits would it take to give us 16 values? You tell me in the chats. How many binary bits would give me 16 values? What do you think? Yeah, it's 4. 2 raised to the power of 4 is 16. So each hex digit contains 4 bits. And we have 4 bits in a hex number, and we've got 4 hex numbers in a quartet. So 4 times 4 is 16. And we've got 8 quartets, so 16 times 8. That's where we get the 128 bits. Now, one of the claims to fame when you're reading the literature about IP version 6, and I think this is kind of funny, they say one of the great things about IP version 6 is it doesn't do broadcasts where something just goes to every device on the network. And it's true, there's not something where we just set everything to a 1 and it goes everywhere in the subnet. No, that doesn't happen. But IP version 6 does have something called an all nodes multicast. And think about that, an all nodes multicast. It's a multicast, wink, wink, but it goes everywhere. Sure sounds like a broadcast to me. But yeah, it's an all nodes multicast. So yeah, technically we don't do a broadcast, but if we needed to, we could. Something else that's kind of a claim to fame for IP version 6 is that you don't have issues with needing to set your MTU size or have problems with MTU sizes. Let me back up. If you got 2 routers and their maximum transmission units are different, then one side might be sending a 1500 byte packet and the other side's MTU might be set to 1478 bytes. Well, if it's unable to receive that, it's going to say, well, this 1500 byte packet's too big. I got to fragment it. I got to break it in 2 and then stick another header on each of these fragments, and it has to be reassembled at the far end. It adds bandwidth overhead. It adds delay. Not a good scenario. So you got 2 IPv6 devices talking to another. Before they start transmitting, they'll negotiate. They'll negotiate the MTU. And that way, fragmentation is almost eliminated. Now, let's take a step back and focus on hexadecimal numbering, because that's really what we have to deal with when it comes to IPv6 addresses. Because I said, yeah, we still have to write out 32 of these hex digits, even if we're using hex. Is there a way to shorten those? Sometimes. I want to give you 2 rules for shortening an IPv6 address. Rule number 1 is, if there is a quartet, one of those groups of 4 hex digits separated by colons, if there's a quartet and it begins with a 0, you can leave out the 0. If it begins with 2, you can omit leading zeros in a quartet. Now, if you had a quartet that was all zeros, you would eliminate the first 3, and then you would have a 0 there. Or you could do this. Here's a second rule. Let's say that we've got more than one quartet in a row that contains all zeros. Notice in this address on screen, it's the, let's see, 1, 2, 3, quartet number 4, 5, 6, they're all zeros. So would I have to say :0, :0, :0? I could do that. That's valid. But if I've got contiguous all 0 quartets, I can represent all of them with a double colon. That's going to be a big time saver for me. I'm going to represent all 3 of those just with a double colon. Now, let's say that you have a couple of all 0 quartets stuck together at the beginning of the address somewhere, and then there's a couple more down here. You can only do the double colon trick one time, because you've got to have 8 quartets. And if you've summarized 2 quartets here and you've summarized 3 quartets here, you don't know how many you're summarizing in each spot. So the double colon trick only works one time per address. But let's see if we can summarize this one. Let's take a look at it quartet by quartet. We begin with 23A0. Does not begin with a 0. There's nothing to abbreviate, unfortunately, so we just got to say 2380, or 23A0 for the first quartet. And for the next quartet, 2018. Again, we do not begin with the 0, so we just got to bring it down. Nothing to abbreviate there. But look at the next quartet. 00B2. We can eliminate those 2 zeros. So now we can say :B2. We just got rid of 2 of our hex digits. We're making this thing smaller already. And then check this out. My next quartet and the next and the next, they're all zeros. So what I can do is I can abbreviate all 3 of those with a double colon. That's going to be a huge savings. So a double colon represents those contiguous all 0 quartets. The next quartet begins with a 0. It's 0400. I can eliminate the leading 0 and just put 4000. And the last quartet, 0001, :1. And the /64 says that my prefix length is 64. That's the number of bits in my network. Let me give, and this is not for a prize, but I just want to give you a practice of doing this. Now, here's what I want you to do. I want you to chat this in. I want you to give me the best abbreviation for this. There's more than one correct answer. I want you to give me the most abbreviated form of this address. And go and chat it in when you get it done. Started to get an answer or 2 in. Looking pretty good so far, actually. All right. Most people are agreeing, so let's go through it together. That first quartet, it does not begin with a 0. There is nothing to abbreviate. Now, the next 3 quartets, they're all zeros. Aha! I could use my double colon trick here, but not so fast. I need to look further down in the address to make sure there's not a better opportunity to use it. And as I look further down in the address, look at that. I've got 2 more quartets that are all zeros. I can abbreviate those, but I can only do this one time. Is it better to abbreviate 3 quartets or 2? Yeah, I think you would agree that it's 3. So yeah, this is the place to do that. So I'll do a double colon, and then in the next quartet, 1, 2, 3, 4 does not begin with a 0, nothing to abbreviate. And the next 2 quartets, I cannot do the double colon trick. I can just eliminate all but the last 0. So I can say colon 0 for the next 2 quartets. And then we end up with 0, 0, 0, B. And I can eliminate those leading zeros and just say colon B. And slash 64 for my prefix length. And I would guess about 70% of the people got that right. Excellent job. Now, just as a reference for you, I said this out loud earlier, but I want to make sure you can visualize it. We've got our base 10 numbering system. I'm counting 0 through 15. I'm using 4 binary bits for my base 2 numbering system, binary. With 4 bits, I can represent 16 possible values. And you see all 16 of those values. And then we see the base 16 numbering system, which is 0 through F. So a 10 in decimal, that's an A in hex. An 11 in decimal, it's a B in hex. All the way through 15 in decimal, that's an F in hex. And we're going to need to do some conversions here. Now, a single hex digit, we can see, represents one of 16 different values. And one hex digit can be represented as 4 binary bits. Now, here's a term that you may or may not have heard before. Now, we've heard of the term byte, B-Y-T-E, but it kind of sounds like you're taking a bite out of something. Well, what would be a smaller version? Instead of taking a big bite out of something, what would you call just a small bite? You're taking just a sampling of a sandwich. That would be a nibble. Well, a byte is 8 bits. A nibble is less than that. A nibble is 4 bits. So each of these hexadecimal digits represented with 4 binary bits, those bits are a nibble. So if we combine 2 nibbles together, that gives us 1 byte. But here's the challenge. A 6 let's say that I had the number 22 in hex, and I had the number 22 in decimal. They both look like 22. But they have very different values. They have very, very different values. So how do we say that this is a hex number and not something else? Well, generally, we prepend a hex number with 0x. The 0 doesn't really have, and the x, they don't really have any meaning except to say, hey, the number that I'm about to show you, it's a hex number. So if I had 22 in hex, it would be 0x22. That tells me it's not decimal. It tells me it's a hex number. Let's do some conversions, shall we? Let's convert the decimal number to hexadecimal number. Let's convert 241 in decimal. Let's convert that to hex. Well, to do that, we need to break that down into all the bytes and the nibbles. So we're going to convert 241 into binary. We learned how to do that about an hour and 45 minutes ago. We're going to convert 241 to binary, and I'll not go through the whole set of questions. We did it a few times. Is 241 greater than or equal to 128? Yes, put a 1, find the difference, take the difference to the next column. We did that plenty of times. But we're going to convert 241 to binary. And when you do that, it comes out to 11110001. That is a byte. It's 8 bits. We're going to take those 8 bits, that byte, and break it into 2 nibbles, 2 4-bit nibbles. So the first 4 bits are 1111. The last 4 bits are 0001. Now, we're going to take each nibble and write its hexadecimal equivalent. For example, if I were to look at 1111 in isolation, if I said, okay, 1111, if I were to look at that in decimal, that's a 15. 8 plus 4 plus 2 plus 1. Well, that's going to be an F in hex. If I look at 0001 in binary, well, that's a 1 in decimal. That's a 1 in hex. So I convert a 15 into an F, and I convert a 1 into a 1. It's a hexadecimal 1, though. So now I have an F and I have a 1. But I don't just want to write down, oh, it's F1. I need to say, oh, this is a hexadecimal number. It's 0x, which says, attention, the following number is a hex number. We write 0x F1. So 241 in decimal is 0x F1 in hex. Let's have you do one. This one is not for prizes. This is for your practice. But I want you to take the decimal number of 198 and tell me its corresponding hex value, if you will. This might take you about a minute or so. So chat it in when you get it. 198 in decimal, what is that in hex? And please don't use a scientific calculator. That takes the learning out of it. That's the reason when I'm doing the prizes, I'm having you give some extra information just so that you're not asking ChatGPT the question. I'm seeing the first answer come in from Jim. Let's see what everybody else says. MJS agrees. Brian agrees. Oh, no, Brian does not agree. We've got to vote for 0x C6, C2, and we got a bunch of votes for 0x C6. Let's go through it together. I'm going to assume that you were able to convert 198 into binary, and it came out to be 11000110. We're going to take that byte, break it into the two nibbles. 1100 is going to be one nibble, 0110. It's going to be our other nibble. Let's convert each of those into what they would be in decimal. 8 plus 4 is 12. 4 plus 2 is 6. Let's now convert the 12 into hex. So if an A is 10 and a B is 11, then a 12 would be a C. So the 12 is a C and the 6 is simply a 6. And we prepend that with a 0x. So the answer is 0x C6. And yeah, most people got that correct. Yeah, and Brian got that corrected as well. So 0x C6. Let's go in the other direction. Let's take a hexadecimal number and convert it to decimal. If I've got the hex number of 0x2f, what is that in decimal? Well, let's take each of those hex digits, the 2 and the f, and let's write those as a 4-bit value. So if I take a 2 and write that in binary, that's going to be 0010. And if I take the F, that's a 15 in decimal, that's going to be a 1111. Well, I'm just going to join together. I'm going to concatenate that value. And that's going to be 00101111. And then I take that 8-bit binary number and I convert it into decimal. I add up the column headings containing a 1. 32 plus 8 plus 4 plus 2 plus 1. It's 47. Yeah, a lot of people chatted that in ahead of me. Awesome. Let's have you do one. I want you to take the hexadecimal number of 0xBC and tell me what that is in decimal. All right, 0xBC and go. What is that in decimal? Yeah, it does take a little bit of time. Haven't seen the answer come in just yet. Actually, yes, I have. I was looking at the wrong screen, or looking at the wrong place. My apologies. So yeah, we do have some answers coming in. Let's see if we agree. First of the thing, we want to represent each hex digit as its binary equivalent. So a B, we know that's an 11 in decimal. If we were to write that in binary, that's going to be 1011. A C, that's going to be a 12 in decimal. We can write that as 1100. And we just concatenate, or we join those together, and it's going to be 10111100. We put that in our 8-column table, and we add up 128 plus 32 plus 16 plus 8 plus 4, and that gives us 188. And looks like, trying to scroll up to make sure. Let's see, Jim got it. Was anybody before Jim? Yeah, things are scrolling pretty fast here. I think Jim K may be the first one with the correct answer. Congratulations to Jim, or whoever got it right. All right, folks, let's take our final pop quiz of the day. This one's about BB-8, but here's the requirement. I'm going to ask you to give me a hexadecimal, or I'm going to ask you to give me a binary value. I want you to give me a binary value for a hex number. Now here, I'm not saying it has to be just 8 bits. In fact, it's not. It's going to be 12 bits long. I want you to give me a 12-bit binary number. But let's say that I said convert FE2 into binary. I don't want you to just say it's all these ones and then 0, 0, 0, 1, 0. I want you to say, oh, well, the F converts to these 4 bits. The E converts to these 4 bits. The 2 converts to these 4 bits. So combined, it's these 12 bits. I want you to show your work. All right, are you ready? Let's go for it. Your BB-8 droid needs to send its identification in binary. What is the binary equivalent of the hexadecimal number 0x BB-8? So give me BB-8 in binary, if you would. B equals 11 in decimal, and 11 is 1011 in binary. Same thing for the second B. And an 8 in binary, or hex, is an 8 in decimal, and that's 1000 in binary. And those 3 nibbles combine to 1011, 1011, 1000. Thanks, everyone. See you next time.